we're going to talk about how a database works, right? I thought I'd bring along this book because I think a book is a good analogy for how a database works.
Okay.
There's a couple of things that this book is similar to a database. One way is the content of the book is divided in chunks, where a chunk is a page. So every page has the same size.
Right.
So even though you can think of all of the content of the book is just one long contiguous stream of words, at the end of the day, you still have to divide them up into pages.
Right.
And so there's a discrete number of pages. The database works the same way. All of the data within a database are stored on pages. They also call them pages. Sometimes they call them blocks as well. Let's say the database has a whole bunch of records.
Like each row is a record.
Yes, each row of a database table, let's say, is a record. This can be seen as a long contiguous stream of information. What the database is gonna do is store it into fixed sized pages. So maybe a page is like this. As many pages that are needed to contain all of the stuff.
How does it know which page?
Yeah. So, good question. The reason we do this, separate things into fixed size blocks, is because it's much more predictable to make assumptions about how long it takes to save a fixed size chunk onto the disk. Another reason is because there are actual meaningful sizes. The physical hard drives that we use, they have actual physical disk sector sizes, which I believe is like 512 or something. That's the smallest unit of data you can read or write from a disk. If you want to read anything at all, you at least have to read that much. And also operating system use this concept of fixed size blocks in the workings of the operating system as well. So when you're reading a file from the disk, the operating system is gonna make one page, allocate one page in the operating system and put stuff in it and then give it to your program. So it's like, might as well use pages to match up with what the operating system is doing. Your question is, how do you know
where to put it?
How do you know like what record goes on what page?
Exactly.
Right. So another thing about the book is that it's got this table of contents. Where is it? Yeah. This table of contents is like your primary index, right?
Okay.
The primary index is basically laying out for you the order of the content in the book, and in the primary way that it's organized.
Right.
In a database, that's equivalent to a primary key of a table. If you're looking for a particular section, you can either use the section number or the page number to find the actual page. Which kind of answers your question about how do you know where the record is, given like you want a particular record and you know the identifier for the record. If you don't know anything about the database, look through the table of contents, which is your primary key. I guess when you're dealing with an application that reads from a database, you can also just list all of the things. Or you already know a primary key. If you already know a primary key, it would be you already know the section that you're looking for. I want to learn about greedy algorithms, so you look it up in the table of contents, and then that's your page number.
Okay.
And which is exactly what the database has as well. The database also is going to have a primary index. The primary index of a database also has to fit into these pages as well. So just like a book.
Okay.
So there are pages that are, dedicated to storing the table of contents or the primary index.
Okay.
and then the database also has to keep track of where those pages are versus the pages that store actual content. There's also a secondary index in the back of the book. There it is. So yeah, the secondary index is a sorted list of the concepts that are notable that were covered in the book, right? So you could look through the secondary index, and in the database, the secondary index would be something like index for foreign key or just a title. Like you want to be able to search by the title. And so you put an index on the title, and that would be your secondary index. So a database can have a number of secondary indexes for a given table.
What if you index everything? What will happen? Is that
Index
make it really fast to search anything?
Okay, good question. So we have a user table. We have 4 columns, and we were saying, basically, like, should we just index all the columns so that searching for the user by any column would be fast? What that amounts to is you end up creating one secondary index for each column, so similar to the one at the back of the book. So you just have 3 of those instead of just 1. But the cost of doing that is you have there's some work that needs to be done to maintain the indexes. Every time you update a user or any number of users, you add a user, delete a user, modify information about the user, you need to keep those indexes updated. That's not a problem for the book because the book does not change.
Right.
For database, that is a problem, and let's think about now how the database maintains those indexes. If the database store the indexes, this is one of the secondary indexes.
Right.
Let's say this was the secondary index for a username, which means, well, if you add a new user, it has to add an entry in this index. You go alphabetically to find where the email address of the new user should go in. And you actually have to make room.
So if it's stored in this format, you have to push all the stuff behind it.
Exactly. So like the user is Emily. We're gonna stick it somewhere here, somewhere in here. We have to make room to put Emily in here.
Right.
All the entry after it has to shift down in this page, and that means all these pages have to change. And this is a pretty big index.
What if they use
so that's actually a pretty expensive.
What if they use a linked list?
Will
that work?
Yeah, that would be cheaper.
Okay.
So yeah, now we're talking about choosing data structures.
Right.
The design of the database is very much reliant on like the data structures, the algorithms that you use. How are we going to store the index? We could use an array, and if we use an array, we'll have to find the place to insert it, and then once we find that, like all the subsequent entries will have to shift one over just to make room for the new entry. What was the big O of this operation?
It's
where this is n.
I think it's n.
Yeah, it's big O of n because the first just finding this place. Finding this place is log n because you can do binary search there. So but the shifting is n. And then so the time is like n plus log n, and because log n is small compared to n, we don't care about this guy, so we just say this is a big O of n. Let's do a linked list.
You don't need to shift.
Exactly. You don't need to shift in a linked list.
But you still have to find it.
Exactly. So in a linked list, you're gonna find where to insert the entry, and then you don't have to do this shifting thing, because you can just change this pointer to point to the new thing.
Right.
That's the new thing. point, and then you have the new thing point to the next thing in here. So what's the big O of this insertion? So this is a linked list.
Well, that's one. Well, you when you find it,
Exactly.
well, then you have to go through everything to find it. You don't
Exactly.
have log n, so that's n.
Whereas with the array, we could find it in log n time.
Yeah.
With the linked list, we have to find it in n
N.
time now.
Okay, so
so there's still n
Okay.
n plus big O of 1,
Yeah.
which we still have n, but it's probably gonna be better because the copy operation is gonna be more expensive for just looking through.
Right.
So linked list version would be better than this version, but still it's still big O of n.
Okay.
So obviously we want something that's better. There's two better strategies. One is the hash table,
Okay.
another one is the tree. Wait, the hash table doesn't really work now that I think about it. Hash table doesn't work with ordered values.
Okay.
Let's just talk about the tree. This is sorted alphabetically, but we don't have to. This is not the only way to sort things. We can think of sorting as in things are sorted into bins.
Oh, I know the tree you're talking. Where is it?
So one way is like we can say, we're gonna divide up the index into 26 bins,
Okay.
one for each letter in the alphabet.
Okay.
Etc. into Z, and then all the A's are in a bin,
Okay, and then that's the second letter.
and all the B's are in a separate bin, all the C's in a separate bin. So I know Emily is gonna be in the E bin, and if the E bin was just an array, then I could go do the same thing as I would do here to the E bin. But we don't have to stop here, because we could say, hey, you know what? I'll divide this up into bins for the second letter.
Okay, gotcha.
Right? We don't have to stop here.
Oh.
So I can do A, B, C, D all the way until Z. And then we could keep doing this for several levels.
Okay.
And that will make the search really fast, right? Because if you do 3 levels or 4 levels, you can imagine, well, at the end, you don't have that many things left that are all start with E, M, and I. So this is why the tree works. And this is how you can conceptualize it. But this scheme using the alphabetic letters, that's a very static scheme. As in, I'm organizing things by the alphabet letters like this. But it doesn't have to be like that, because this may not be the most efficient way to divide things up. Maybe your system has a lot of E's and no A's at all.
Oh, okay.
And then I'm kind of wasting space over here. So a more dynamic scheme following the spirit of this, but without having it be predetermined, like how the nodes are to be organized. And that's what a binary tree does, and it's also what a B tree does. I think it's easier to just talk about the binary tree. For this purpose. The B tree is a little more complex. This is a valid binary tree, the binary search tree, BST for short. In order for your binary tree to be a valid binary search tree, it has to satisfy the property, which is that for every node in the tree, this left child has to have a smaller value than the parent, and the right child has to have a larger value than the parent. And that property has to be satisfied at all times while you're working with the tree. And it's the job of your algorithms. Your algorithm that have to modify the tree have to make sure after every modification, that property is satisfied.
Okay.
So there's like a family of algorithms that work on this tree that has to maintain that. Now I put numbers here because usually that's how they're taught. How you put number here, but these doesn't have to be numbers. This could be a string.
Okay.
Or it could even be a user record
Okay.
that goes inside the binary tree node.
Okay.
All it matters is that there's some way to compare the values between two nodes. And you can tell me, given this versus this, or this versus this, or this versus this, is one of them greater than the other, or are they equal? That's all that matters. This is how an index is actually represented in a database. And when you insert a new entry into this index, such as Emily, let's pretend Emily is 11.
Okay.
But like I said, these could be strings too. So
Okay.
you could just insert a string, Emily. But let's pretend Emily is 11. So if you're inserting 11 into this binary tree, you're gonna find where it needs to be. And
We go to the left.
so you start from the root of the tree, and then you're gonna go to, if 11 is smaller than that node, you're gonna go left to get to 5, and then because 11 is greater than 5, you're gonna go right, and then because 11 is greater than 7, you're gonna go right and stick 11 right in here.
Oh, then you can do a login.
Exactly. This is a login insertion because you made as many hops as the height of the tree. N is the number of nodes in the tree. The height is gonna be the log of n. So you had to traverse proportional to the height.
What about to find a node? Is it
To
also
find-
login?
Yes,
Yeah,
the
okay.
final node is also log n. If I wanted to find any number in this tree, or even a non-existing number, to figure out whether that it didn't exist there, I do the same algorithm. If the thing I'm looking for is smaller, I go left. The thing I'm looking for is greater, I go right,
Okay.
until I would get to the leaf of the tree, where I will either find it
Gotcha.
or find that it isn't there.
Gotcha.
So that's also log n. So
That's pretty nice.
that's the beautiful things about trees in computer science. The trees really is like my favorite data structure because the tree is a trick that allows all of the common CRUD things you do with data structures to be log n time.
What if this tree is always goes like one way, like this? What if all the numbers go this side? What will happen?
Yes, there's a
And
common
this will
problem.
get-
You're basically pointing out the problem that we can only enjoy this benefit if the tree is balanced. Because it's possible for any tree node to not have children. The left of 10 is null, and the right of 10 is null. So, given that, it's possible that we, instead of getting something like that,
You will get
We-
a linked list.
we might get like if you insert 1, if the root of the tree is 1, and then next you decide to insert 3,
Right. And then you get 4 next.
and then the left of 1 is null,
Right.
and then you decide to insert 4, and you're like, oh, where's 4? Oh, 4 greater than 1, so go right. 4 is greater than 3, so go right, and so forth. And this side is null, and then you insert 5 and so forth. So it just keeps on going only to one direction.
Yeah.
And this is
linked list.
this is unbalanced tree, and we don't get to enjoy the benefit of getting log n time because we're not using the left side of any
Right.
of the tree nodes. This is equivalent to a linked list. So one thing about this is computer scientists have discovered that if you do this in order insertion, like if you insert the nodes in the order of the values, you will definitely have this problem.
Oh yeah.
However, if you insert these guys in a random order, then usually you don't have a problem. Usually you have a pretty balanced tree, kind of like this.
Okay.
So there's one concept that tries to solve the problem using random number generation. It's like, what if these were inserted randomly? There's several ways. There's several schemes, and this might still be an area of research of algorithms that make sure the tree is balanced. And one of those ideas is red-black trees. So red-black trees is one of the famous ideas. There's a whole chapter dedicated to red-black trees. I'm not gonna go into too much detail because it's kind of complicated, but I'm just gonna explain the gist. We're gonna color each of the nodes of the tree either red or black. In the book, it's actually black-gray trees because there's a black and white book. But anyway, similarly to how in the binary tree, there's that property that always have to be maintained for it to be valid. Red-black tree has an additional 5 properties that must be maintained in order for the tree to be a valid red-black tree. Every node is either red or black. Okay, that's easy. The root must be black. Every null pointer is interpreted as black. If a node is red, then both its children must be black. And for every node in the entire tree, all paths starting from that node to the bottom leaf must contain the same number of black nodes. Like if I start from any node in the tree, should I count myself or not? Okay, anyway, if I don't count myself, it's 1, 2, 3 here, 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 1, 2, 3 here.
Well, it must be complicated to keep it up.
Yeah,
Well,
the people who invented this concept, they gave you an algorithm. As long as you implement the algorithm correctly, there's an insert procedure. If you follow that algorithm, it'll guarantee that this is maintained. And to give you an idea of how that works, so if you insert a new node, which is Z, you're looking at your parent and it's like, no, my parent is red, I cannot be red. I must be black. So it does a change to the tree. So what it does is, it just made both my parent and the sibling of my parent black. To maintain this. And then what's more, yeah, exactly. Then the parent has to change color as well. You keep moving the change up the tree. So it could potentially propagate like more and more changes all the way up to the root. So the result of adding this 4 here required 3 separate steps propagating a change up the tree. In the second step, it actually moves some of these nodes over to the left. It's called a rotation. And that's kind of how the tree automatically keeps itself balanced. Sometimes this is too heavy and you have to move some things over. And then here it actually moves some of this stuff over to the right side. So now it's actually, you can see it's much more balanced because as the end result of this algorithm, there's this 7 actually got moved up to the root. The 7 used to be here. It got moved up to the root.
But
eventually.
Would that be more than like log n? Because you spend log n to insert the 4 right here, and then you do all these.
Well, this propagation can at most propagate up as much as the height of the tree.
Okay.
So that's it's 2 times log n. Or constant 1 times log n plus constant 2 times log n. So at the end, you still get log n.
Okay, gotcha.
So this is, so even adding the cost of maintenance of the tree, you still get log n.
Nice.
And that's I guess what we're after. But still, there are other algorithms, other schemes other than red-black tree. So anyway, so that's how this kind of this tree maintenance stuff. It's actually kind of hard computer science stuff, but it's, there's well-known literature about it, and you can learn it.
The person who invents this very smart because they came up with solve this issue.
Yeah. So at the end of the day, so if we can assume that we have algorithms that keep our tree balanced like this, we can be guaranteed a log n time for inserting into a tree, which we're gonna use for an index, right? So we don't have to worry about the updating of the index being slow. If we decide to index a lot of different columns, updating a user or inserting a user or deleting a user, we'll have to go in and update maybe one or more of the indexes, and each one will take log n time. However, that can still add up though.
Okay.
Even log n time, if
That's true.
you add up a lot of those, can still be a lot.
Right.
So that's why we don't tell people just index everything.
Okay. Gotcha.
Okay, now let's talk about like how do these indexes go on pages.
Wow.
That's the last thing we'll talk about. Databases use B trees, which is like a binary tree, except that every node can have more than one children.
Okay.
Like the fan out is much greater.
Okay.
Which is also nice because any number, if you find how the height of the tree in base 2 is a certain height, if you use a larger base, the height is going to be much smaller.
Right.
So which is nice to have a larger fan out. What the database does is use an entire page as one of these nodes of the tree.
Okay.
So a page, let's say a page is 124 bytes. So I'm gonna store the key plus plus each child of the tree, which there can be more than 2.
Okay.
So first I'm gonna store my key, and then these are pointers to other pages,
Okay.
which are my children.
Okay.
So, and then each one of these are gonna be a page. And because each one of these is only an address, the fan out here could be really, really large. I have 124 bytes here.
Right.
I could store a lot of addresses here. This could be 100, even 1,000 pointers to other pages. But conceptually, it's exactly the same as a binary tree.
Okay.
It's just the fan out, it's much bigger.
Okay.
And from a operational standpoint, you can think of it as, well, in order to walk down one level of the tree, I have to get the next page, which sometimes requires me to read a block of data from the disk.
Okay.
If it's not already in memory.
So it's like each time you walk down one step to the tree, in the binary search case, it's just you either go left or right. But this case, you can have much more options.
Yeah. So you compare the thing to 12. Actually, okay, this is not accurate. Next to each of these pointers, there's actually also a number. So this might be, I don't know, 24, 26, 27, right? Each number is pointing to, like, if it's less than this number, then go to this page.
Okay.
If the key you're searching for is in between these two numbers or something, then go to this page. If it's the next, this is marking these ranges basically.
Okay.
So it's within this range, go to this page. Within this range, go to this
Okay.
page. Within this range, go to this page. Whereas this is just greater than or less.
Okay.
Yep.
Would like a database like a NoSQL database, does it work the same, or it will be really different?
And NoSQL databases work the same way.
Okay.
This is true of both.
Yeah, I guess it takes people time to invent algorithm like this, so that they can read and write really fast.
Yeah, there's many years of innovation in computer science before.
Yeah, because before we have computer science, just think about, you have like library, right? If you have a library, then you have a lot of books that you have to make a system so that you can quickly find a book.
Yeah, libraries came up with
Right.
their own system, and that there was a lot of years going into figuring that out also.
Exactly. Well, I think it's a similar system.
Yeah.
It's like they have like a letter that's based on the category of the book, and then there's the next letter, it's based on the subcategory of the book, and then there's the next letter.
Mm-hmm.
Yeah. So it's similar to this idea.
Yeah. Yeah, and the binary tree and the B tree is they're not using a predefined number to figure out how to go to the next level. They just figure that out dynamically based on the data that's coming in.
Yeah. Cool. Thanks. This is nice.
You're welcome.